I'll sleep on the airplane.
I was thinking of choose the same city.
All right. Good morning. So we have. Oh, well, yeah. I yeah, that was a hot day. You don't need to see pucks of time. So anyway, right. So right, your number 3 is due today, and problem 4 is coming. As I close, I promise I'll record a little video to explain the problem, so you can make sure having them in Alejandro, I'll discuss it with you after class. Okay. And so exam. The first midterm exam is happening not next week, but the week to follow. It'll cover through problem set 3. It'll just be on electrostatics. And I'll talk about it more next week. Okay.
So chapters 1, 2, 3, or I guess monopoles are 4, right? Or...
Yeah, I mean, it's the material. I'll give you explicitly, you know, what is through lecture 6 of the notes, and then whatever supplementary material in the textbooks that you're using. Okay. But it will basically cover electrostatics.
This exam's a little bit early for a midterm, so are we going to have 2 midterms?
You are. Okay. They're not midterms, they're in-class exams. And that's what so there were two, there will be 2 exams and a final exam. You can call them midterms, but they're third terms and 2 third terms. And the final exam will be weighted more heavily on the material that we will not have tested on, but it will be cumulative because, you know, it's not like this is so compartmentalized. All right, very good. So last time we talked about, we started just to remind ourselves about magnetic fields and magnetostatics. So importantly, there are forces on charges that are not just due to electric fields, but also due to magnetic fields, and those forces arise proportional to the current. So that is to say, a moving charge will experience a force due to a magnetic field, okay? And that's the Lorentz force law, written in the familiar form of a point charge up there, but more generally, if we have a distributed charge and current density, then we have a general form of the Lorentz force law, okay? And an important fact of life is that charge is conserved. And as I discussed, we'll talk about varieties of conservation laws in electricity and magnetism. Charge is conserved, but of course, also energy is conserved, momentum is conserved, angular momentum is conserved, and how we describe the conservation of all of those quantities in electricity and magnetism as the fields themselves carry momentum, energy, angular momentum, for example. And so the mechanical energy that is stored in the charges can be transferred to the energy in the field, and vice versa. You can absorb energy from the field and then be excited. Whee! Yeah, that's my inspirational excitement. Right. So a general conservation law has this form. The change of the stuff enclosed within some volume, in this case the stuff is charged, the only way it can change is not because the stuff is created or annihilated, but because it's moving from one place to another. So that says thus that the change of the charge enclosed in some volume sense, has got to be equal to the rate of change of the flow out. That's to say, it's the current in. So the volume is how much the charge is changing. And so that relates locally at any position in space how the charge density is changing. And it's changing related to the divergence of the current density, okay? So this equation of motion is as a general form of a conservation law, say for fluid flow, or in this case, charge flow, or energy flow, as we will see, right? So this will take the form of Poynting's theorem, as you may remember from your undergraduate days. We'll come back to that, but just sort of, keep that in mind, okay? And this is a general expression of conservation of charge. The magnetostatic case are the situations where the charge density is not accumulating anywhere or dissipating in any way, but just flowing in a steady way. So a steady flow of charge, a steady current, is the case where the charge is not changing, density is not changing, and thus the current density is neither converging nor diverging from any point in space, okay? So that's the condition of magnetostatics, okay? It's also consistent with the conditions for electrostatics, because in electrostatics, the charges don't move at all, ever, in any way. They don't flow, they're just fixed in space, but that's consistent with the charge density being constant, okay? All right, so now the empirical law that describes how magnetic fields are created by the source, and the source of magnetic field is current, at least classically. Quantum mechanically, we also have spin, which is not really a current, but it's kind of like a current, but just keep that in mind. And so classically, though, a flowing charge creates a magnetic field, and this is the Biot-Savart law, which is a kind of, looks like Coulomb's law, but with cross products and vectors, okay? And from this, we kind of went backwards, said, well, if this is the equation, these are what the magnetic field, this is the field equations for the magnetic field. That is to say that if we know the divergence and curl everywhere, I mean, they have no other boundary conditions that we have to satisfy, that tells me the whole story, other than the thing is 0 at infinity, right? And so, these are the differential forms, the integral forms. Says that if I look at the volume integral of this, I can use the divergence theorem to tell me that the flux of the magnetic field through any closed surface is 0, okay? And in contrast to the electric field, where we have this proportional to the electric charge enclosed via Gauss's law. So this is an expression that there are no magnetic charges enclosed in any volume, even if that volume is big. So this is there are no magnetic charges, which are also known as monopoles.
That we've seen consistently.
That we've ever, that we can say with a repeatable experiment.
Yes.
Yeah, that we, yeah.
And that comes from Biot-Savart law. Doesn't permit magnetic monopoles.
That's right.
And when we work it out, we get to the differential equations there.
That's correct. Now, it's sort of induction versus deduction kind of sense of the word. I mean, in some sense, we like to think about it the other way around.
Right.
That these are the fundamental equations and we can test them.
Right.
But the way, in some sense, they were arrived at was through the empirical work of Biot and Savart, or maybe that's one person, I should find that out. Yeah,
So if we did happen to come up with a repeatable experiment for monopoles, nothing would break, we just add an extra term.
that's correct, that's correct. So there would be a Coulomb-like law, and for the magnetic field, and there would also be an electric equivalent of Biot-Savart. The current of the magnetic charges would also create, if there was a steady flow of magnetic charges, that magnetic current would create an electric field. So there would be a more parallel structure. Right. Both of those would be modified.
It's really fun to see the modified version of Maxwell equations that allows for monopoles. Everything's so symmetric.
Yeah, it's like supersymmetry, wouldn't that be nice? But yeah, one of my ears is a little different than the other. Something that only drives me crazy. All right. Right. So what was I saying? Oh yeah, this. So the integral form of course, this is the Ampere law. Would say, if I look at the surface integral of the curl of B through a bounded surface. So I have some surface, a potato chip, that is a orientable surface, meaning it has a direction normal to the surface. That's the surface. And there's a contour that is the boundary of the surface, okay? And it has an orientation according to the genetic preference for the right-hand rule, okay? So according to the Stokes' theorem, yeah, that's the person. This is equal to B dot dl, the circulation around that contour. But according to that, this is equal to 4 pi over c, the surface integral of j dot n j, which is, if there is current density flowing through here, there is a certain amount thus of current enclosed. The current enclosed is the flux of the current density through the potato chip. Okay. Of course, something we all know and have used since freshman physics, that the circulation integral of the magnetic field is 4 pi over c, also known as mu naught times that. Okay? So that's Ampere's law in integral form. Okay? So, as we studied in electrostatics, so now we want to, given a charge and a certain current distribution, a current density, we want to ask what is the magnetic field that is produced by that distribution of current. And we can do that by trying to solve the different equations, Green's functions, and the like. It's harder and nastier for magnetic fields because of the fact that we have vectors and cross products and all of that.
How is Green's function related? Because Green's function was the solution for a point charge.
Yeah, we'll get there. I mean, in the same way, we'll come back to that. I mean, I just wanted to just give the overall, we'll come back to how, to the general solution. But the point I wanted to really just emphasize, as we did with electrostatics, when we have symmetry, and we can use symmetry to just factor out the magnetic field outside this integral from a symmetric point of view, then we can find the magnetic field instantly using Ampere's law without integrating anything or doing a Green's function or doing anything, right? And we all know that. So when we have symmetry, Ampere's law and of course, the symmetry will depend on, you know, what the current distribution is. So the simplest case that we all know is if we have just a line of current, infinite line of current. Of course, no such infinite line exists, but it's just that wherever the ends are so far away that for all intents and purposes, this is infinite, okay? So I have a line of current, okay? And say that it's along, we'll call the axis as we would, there's only one direction, you call it the z direction, because that's always the preferred direction when we're thinking about our coordinate system, okay? And so from this point, we know two things automatically. Firstly, the magnitude of the magnetic field as a function of position. So I'm somewhere, okay? That's my position. We might as well put the origin somewhere, okay? It's the origin. And I mean, I could be anywhere. I could be here, okay? But the question is, if I just think first of all about, I mean, I think about both the magnitude and the direction of the field. The magnitude of the field can only depend on the distance, the cylindrical distance, which I'll call S, from that axis. It can't depend on Z, because where the heck is Z equals 0? I don't know. There's nothing that, there's no point on this because it's an infinite line. And it can't depend on phi, because what phi am I at? There's nothing here. So this has this azimuthal symmetry, the cylindrical symmetry. So this thing can only depend on that coordinate and not z or phi, okay? The other thing we know, if we look at this, is that, okay, there is a direction having to do with the current is flowing in this direction, not that direction, not that direction. So it's flowing in the z direction. And I'm at some direction, so there is another thing it can depend on, which is what direction is the magnetic field can it be in consistent with current flowing like this, right? And what's the answer? Right hand, well, that's the left hand, right? So, right? And that is the phi direction, okay? So what we know from symmetry is that this can only flow in the point in the phi direction. It's the only direction it can point in. And it varies as a function of s, okay? So that means I know how to choose a contour such that b dot dl is a constant, and I can just take it outside the integral, okay? So what I should do then is I should choose dl along the phi hat direction and make the contour be a circle that has the same distance, right? So I should use a contour. So I'm now, because I'm so bad at drawing, here's the current coming out of the page, and here's my contour, which has got a radius s, and this is the phi as a function of s in the phi hat direction, right? And so I should choose my contour to be a circle. And so what that tells me in this case is that and that equals to the current enclosed, which is the current along the direction of the normal and the direction of the normal is chosen by the right-hand rule, so it's the positive current in the z direction, and that's 4 pi over c times I, right? And this is just the perimeter of that, that's 2 pi s. And so the magnetic field associated with around the current that's along the line is equal, in these units, is equal to twice the current over c, falling off like 1 over the radial distance in the phi hat direction. So we know that the magnetic field lines go around this, right? That's elementary, like year Watson. All right? Very good. So let's think about another example, which is less obvious and kind of more tedious, but one which you also know, okay? Let's say I have an infinite cylinder. I'll just draw a finite section of it, okay? And I have surface current flowing around the surface. I can think about that surface current being as a very tightly wound set of coils, right? That. Now, I'm not drawing them so tightly wound because I'm too lazy, but they really should be completely tightly wound so that there's no space between them at all. I'm getting even lazier, okay? And the current is flowing around this thing. We know this is called a solenoid, okay? And there's some unpacking, there's a certain amount of current per unit length. Okay, so the current per unit length here is the current per coil times how tightly I've wound them. So N here would be the number of coils per unit length. Okay. Now, if this is an infinite solenoid, then you can play around with the Biot-Savart, and it's kind of a tedious thing to do. But what we know, what one can show, and this is a shorthand for I'm too lazy to show it. That the B equals 0 outside the cylinder, solenoid, and it's constant inside. Okay. So if that's the case, firstly, in what direction does it point?
It's going this way, then it's going up.
Yeah, so it has the magnetic field itself has to point in the z direction. And it doesn't depend on where I am as a function of z, because it's infinite in length. If it was finite in length, that would be a different story. So let's then draw a cross section of this thing, and I got current coming out of the board here, and let's see which way am I? Let's see, hold on a second. So the current is going, yeah, it's going out of the board there, and it's going into the board here. Okay, that's a current. That's just a cross section of the solenoid. Okay? And I want to find what this magnetic field is. I know it's in the z direction, and I know inside here, I know it's 0 outside here. And I know thus that I can write it's 0 outside, I can choose a contour on which the magnetic field B dot dl is constant. What contour should I use in this case? I want to calculate what the magnetic field is inside the solenoid. Well, we know the magnetic field is pointing in the z direction, so I should choose a contour that's points along the z direction. It has no component like this, right? And so I'm going to choose my contour that goes like this. Okay? So, what is the circulation integral of the magnetic field around that contour? Well, it's V dot dl, which is the same along that. We'll give it some parameter L. And what's the contribution along this? 0, because that. And what's the contribution along this? 0, because there's no magnetic field. And what's the contribution along this?
12.
No, wrong, Benny. What is it? It's 0, right? And what thus is equal to the 4 pi over c times the charge enclosed. But what's the charge enclosed here?
Current equals, it's n times I.
That's right. A little n is the number per unit length times L. Okay? So, with that said, we have that the magnetic field inside the solenoid is equal to 4 pi over c times I times the number per unit length inside and 0 outside. Very simple. Okay. Question. I have a very similar problem. Suppose that I had this infinite cylinder and I pasted upon it a surface charge density, a charge per unit area, okay? And then it's spinning around with an angular velocity omega. What's the magnetic field inside the cylinder? Yeah.
4 pi over c in.
Well, what is IN in terms of these parameters? You're right, it's the same thing.
Sigma.
It's the same thing. This is a solenoid. But what we need to, so I times N, we said, is the surface current density, right? This is the current per unit length. Remember, we had this lexicon of things. So the question one of the questions I'm asking you is, what is the surface current density that's flowing here?
Sigma dl.
Not quite. It's kind of depend on omega, right? Now, I need maybe one other piece of information. This guy has sigma omega r, right? I mean, it's sigma omega crossed into our s hat, which is in the phi direction.
Then we need to integrate over.
This is the current density. This is the surface current density. This is the current per unit length. In the same way that this was the current per unit length, right? So if this is the case, if I thought about this now as continuous current, you know, it's a sheet of current going around, making that noise, and then coming through this, what is the charge, the current enclosed, I say, what is the current flowing through this contour, given K? So again, we have BZ times L that's this guy, is equal to 4 pi this, but what's the current enclosed in these parameters? K times L, right? And we just try, again, remember that we have, when we have a surface of charge, it's the current per unit length, and we integrate over the length, as opposed to the current density, which is J times A, okay? Think about it. So, so that's, if I had, and so in this case, that's 4 pi over C times omega times sigma times R. Okay, so that's, yeah.
So for the part of the loop that goes down outside of the solenoid, I get that we know that's 0 by symmetry, but is there a, because to me, like, for each little wire, there's one going inside the board, one going out of the board, but it's closer to 1. So we have to take into account the fact that it's an infinitely long.
We do. It's not a very straightforward calculation, but let me just maybe say, you know, we solved, sort of, last lecture, we had a current loop, okay? And the current loop had a magnetic field that doesn't at all look uniform. But now I stack these up, and I add up all these magnetic dipoles. And what happens is the fringing fields start canceling. So if I were to actually say what the actual field of this actual solenoid looks like, it looks like this. Maybe. Here. So I have a finite. What it will look like, what the magnetic field will look like, oh gosh, there's too many lines. But anyway, I hope you get the point.
Yeah, I guess we zoom out.
So the point is there are fringing fields. It looks pretty uniform in the middle, and as I were to make this bigger and bigger, it would look more and more and more uniform. But near the edges, it wouldn't be at all. In the same way that if we have a parallel plate of charges, we know that if it's an infinite plate, it's uniform everywhere. But if you look at the edges, it's not. And if the distance between the strings is small compared to the size, it's pretty uniform. Does that make sense?
I was just making sure that there wasn't a different argument I was missing.
Yeah, there's nothing more simple that I know of. Yeah. All right, good. Now, one of the things we notice here is that there's a discontinuity. The magnetic field is something inside the cylinder, and then right outside the cylinder is something else. And so the magnetic field is discontinuous. In the same way that we saw that the electric field that was normal to the surface of where you had surface charge density was discontinuous, and we solved for the boundary conditions. Well, the same thing is true in magnetic fields. There's a discontinuity, in this case, in the tangential component. You'll solve for that in homework. All right, very good. All right. All right, so now I want to kind of come back to the question of how do you solve this in general, its functions, and the whole shebang. Let's see, but first I need to find my chart. Oh, here it is. Okay, so if we have the field equations, which are written up here, we want to try to solve them. Okay? Now we have the solution, it's called the Beer-Savart law. We kind of work backwards, but it's not, we rarely would use the Beer-Savart law, it's just too many cross products for any sane person. Instead, in the same way that we did in electric fields, we solve for the potential, which is generally easier to solve for, and then once we have the potential, find the field from the, yeah.
Here's the vector potential.
That's right. So let us remind ourselves. So we have this equation, which tells us that the magnetic field can be written as the curl of another field. Okay? That is the vector potential, as opposed to the scalar potential that we have in electrostatics. Okay? And given that, so this delta B is 0, it implies that. So given this way of expressing the magnetic field, it tells us that the curl of B is the curl of the curl of A, which is what? No, it's not 0. So this is a vector identity everyone is going to.
Laplacian plus something.
Close.
Something minus the Laplacian.
Yeah, it's the gradient of the divergence of A minus the Laplacian. Okay? There is a way to think about that in terms of the back minus cab rule. Think about that a little bit. Memorize that. Okay, we did it. All right. And this is equal to 4 pi over c times j. Okay? So, gee, that didn't look like it helped anything. Now I got a more complicated expression for A than I had for B. So what was the point of that? Well, there is a little bit. So what can we say about A? The vector potential is a vector field defined by its curl and divergence, because by Helmholtz theorem, every vector field is defined by its curl and its divergence everywhere, okay? Assuming it goes to 0 and infinity. So we know what the curl of A is, but what about the divergence of A? Well, the point is it doesn't matter in any way, because the forces which are determined by the magnetic field only depend on the curl of A, not the divergence of A. So the divergence of A is arbitrary. I can choose it to be anything I want. This is known as gauge invariance. The divergence of A in no way affects the physical forces that are exerted on charges. So what this tells me is that if I, let's say that I take A and I transform it to a new A, which I'll call A prime. And that new A I will do by adding something which is the gradient of a scalar field. That's known as a gauge transformation. Suppose I did that. Would it change anything? The answer is no, because what is the curl of A prime? Well, that's the curl of A plus the curl of this thing. Well, what's the curl of that? 0. This field has no curl. So since I haven't changed its curl, I haven't changed the magnetic field. So I can move the vector potential around by adding to it the gradient of any scalar I want. And if I look at the divergence of A prime, well, that's the divergence of whatever A was, plus the Laplacian of this. And I can choose phi any way, this chi, any way I like, because it's a non-physical entity. It's a mathematical extra. And so I can choose it to cancel what this is. And so since this is arbitrary, we fix the gauge by choosing what the divergence of A is at will. Anything we like, anything that's convenient. Yeah?
Can we choose what the divergence of A is and the ground from, like, I know there's a relationship between the gauge potential and
Yeah.
scalar potential. Can we choose both arbitrarily, like the constant?
Well,
or
it's always true that I can add a constant to either of these things. That doesn't do anything.
Mhm.
And in some sense, that's ground. The notion of energy in magnetic fields is a little more complicated. So let's hold off on that concept. But I can add a constant to these fields, and it does nothing because the forces are related to the derivatives. So adding a constant is never a problem. Okay, so what would you, if you had your druthers and you had this equation, what would you choose the divergence of A to be? Well, you can choose it any way you like because it doesn't matter.
0.
0, why not choose it to be 0? That's the easiest choice. So in magnetostatics, we typically, I don't know in any other case that we don't, choose the gauge where the divergence of A is just set to be 0. Because we have that freedom. Freedom! All right, so with that, what that tells me is in this gauge that the divergence of A is equal to minus 4 pi over C J. Okay? That means if I look at a particular component of A, one of the Cartesian components of that, it equals minus 4 pi over C, the ith component of J. Okay? So I ask you, what is the solution to this differential equation? It's one we've seen before. We could use the Green's function. We know this is Poisson equation for each component. Each component satisfies its own Poisson equation in this gauge. Okay? So that tells me that the ith component is what? We remember the Poisson equation. And what's the solution to this equation? No boundaries. I'm listening, yeah? I think you have to integrate. Yeah. In this case, rho is J sub I over C. And then over what? Well, the 1 over r, 1 over the distance. That, we can't forget the easy thing. Don't get confused. Oh, Green's functions are so complicated. It's the field of a point charge, the potential of a point charge, which is 1 over r, 1 over the distance. Right? That's the solution. Or, stated another way, this vector is equal to this vector. This is, in the case, no other boundaries. This is the total charge density, or current density in this case, yes.
So right there, you said we already know the case if J sub I is 0, we have the,
J sub I is 0.
sorry, we already know the case if J sub I is a delta function, so then we just superpose,
Yeah, exactly. This is the green function, yeah. This is the solution to this equation that we just had for any, that we looked at. So this is the solution. Now this problem solution isn't necessarily that easy because of this vector and the fact that the direction of the magnetic field itself can change at different positions in time. I mean, at different positions in space. If the direction of the current depends on where I'm looking, then it's not it's not a simple thing to do. I mean, you can look in Jackson where he writes down what the solution is for the Green's function for a loop of wire, and it's got elliptic functions and it's complicated, and God knows we never use that, okay? So this is, while true, I mean, I don't know if I've ever used this equation other than to do a multipole expansion, okay? Then we use it all the time. So while we, in principle, can use this, it's hard unless the current is, the direction of the current, each one of these things only depends if, you know, if the components depend on position in some complicated way, it's a very hard integral to do, okay? So, yes, you have a question?
I think at the beginning of the class, we already showed that like 1 over distance satisfies the Green's function. So is there any other expression for the Green's function aside this? That's one. And secondly, in magnetostatics, we showed that like the divergence of A is chosen to be 0.
Yep.
I know for gauge fixing, we have different types of gauge fixing.
Yep.
So is it the only valid gauge fixing that we have?
No, it's nothing. Oh, okay, so let me take the last question first and the first question second. In magnetostatics, I mean, there is no law that says I must choose this to be the gauge. It's just the convenient one, because why would we choose it any other way? We would have extra terms to deal with, which would contribute nothing important in the end to the magnetic field. So we always choose this because it's just convenient. But if we could fix the gauge in other ways, as we will see when we talk about dynamics, there's more nuance in that problem. There's what's called the Lorentz gauge and the Coulomb gauge, and we'll talk about all of that. But in statics, why would we choose anything else? We just make our lives more complicated, and your lives are complicated enough, all right? The question about the Green's function is, let me just again remind us that the Green's function, what is the Green's function? I want to emphasize that. What is the Green's function? The Green's function is the solution at x given a point source at x prime. Okay? That's what the Green's function is.
So the Poisson equation.
For anything. A Green's function is I have some differential equation as of some function of x, and I have a source. And what I solve for is what is the solution for that function at the position x given the source at x prime. That's what we mean by the Green's function. Now, what is the Green's function in particular for the Poisson equation? The Poisson equation the Green's function is the potential at x given a point charge at x prime. And the Green's function thus satisfies this, where the source is a point charge at x prime. What is the charge density at x given a point charge at x prime? Delta cubed x minus x prime. Okay, so this is, and the solution to this equation is 1 over r. And given a point charge at x prime, I can find the solution for an arbitrary distribution by the principle of superposition, by just adding up the different contributions from different points in the source. And so the general solution is I have a dq prime. dq prime is dx prime d rho prime. That's the amount of charge at x prime times the solution. Ta-da! So each component of the vector potential satisfies the same equation as the scalar potential, and I just solve it in the same way. Now, this is assuming these are all the charges or all the currents in the problem. If we say, oh, these are the charges I'm going to take into account, but then they have some conductors, and I'm not going to tell you what the charges are, then I can use boundary conditions and all of that stuff.
This is just a general solution to
Yeah.
scalar potential.
That's right. Well, it's, and each component satisfies the same equation.
I see. So you
Yeah.
just have a bunch of these for
One for AX, one for AY, and one for AZ. Yeah.
So, sir,
Yeah.
assuming we are making use of this function to solve for some solution, solve some problems, is it that we normally, what's it called? Agree that our Q is always 1, but what happens to our image charge if our Q is equals to 1 on that Green's function?
Well, the Green's function is a solution for a unit charge, and you can find it for anything else by just multiplying it by the strength of that charge. Okay? This is the Green's function in free space. The other problems we solved in the homework were to say, oh, I have a sphere and I have a charge over here, and I want to find what is the potential at x given a point charge at x prime. That's the Green's function associated with additional charges that are actually on the surface of the sphere. But I don't have to solve for them. I can just use the boundary conditions. But that's another story for a review session where we'll have, because we have other things to discuss, but I want to have more discussions about this to try to clarify that. All right. So where we're going now is we want to talk about the multipole expansion for magnetostatics, which is very important and complicated because of the damn cross products and the vectors. All right, let's see, what am I doing here? Okay, so our problem is similar in spirit to what we had in electrostatics. I have some localized current distribution. In magnetostatics, there's some steady current is flowing around, and it's confined in some region of space, such that outside this region, there's no current at all, okay? So it's, here's my neutron star or whatever it is, but I'm far away from that. Or it's just some blob of stuff and it's rotating around, okay? So I have, and I'm out here, and I want to find the vector potential at x, given the current density at x prime, where this is confined in some region of space such that all the x primes are much, much less than the distance to the point of observation. Okay, it's the same problem we solved in electrostatics, but now instead of having a charge density, I have a current density, okay? And we know the general form of this is equal to, it is written right there. I have to this is the exact expression. Okay, and I want to write a approximation, an excellent approximation to what this vector potential is. Yeah, I know my voice is a little scary. I've been told. In this regime, okay? How am I going to do it? So how did I get the multipole expansion? I do a Taylor expansion, right? So I want to, and we already have sort of done that. So I want to look at this guy under this approximation, right? And this was equal to L equals 0 to infinity, right? Minus 1 to the L that's to the power L. This is the Taylor series expansion of this that we've talked about, okay? And so the lowest order term is 1 over r, and then we're gonna have a minus x prime dotted into the gradient of 1 over r, okay, plus dot, dot, dot. Okay, so we can take this expansion converges well if the length r, which is the distance from the origin to the point of observation, is very big compared to all the x primes that are non-zero in the integral. Okay? So what we get is that this is equal to c times 1r, 1 over that, the integral over x prime, the current, and then I have minus the integral 1 over c d cubed x prime j of x prime times x prime dotted into the gradient of 1 over r plus dot, dot, dot.
Where's 1 over?
Sorry?
I was gonna ask where's 1 over c when you pulled it up?
I pulled it upside, yeah, okay. So I have to do this integral and I have to do this integral, okay? This is a tensor dotted into a vector is a vector, because everything is a vector. Yeah.
Why are we only considering the first two terms again?
Because we don't care about the others. It's more gets more complicated to write it, but I'm just going to look at the monopole and the dipole term and call it a day.
Wait, but monopole thing?
Yeah, well, that's a good question. So we got it. So that but we have a monopole. Oh, Nobel Prize, baby. No, that ship is sailed. So we got to look at this and ask ourselves, what can we say about this integral?
Probably goes away.
It should. So how are we going to show that that's true? I need to remind myself.
It's like crossing it out.
So we cross it out.
Right now, what is that expression? Is that A? That's the vector potential for the first two.
Yeah.
That's just the Taylor expanded to the first two terms. This term goes like 1 over r, this term is gonna go like 1 over r squared, etc. Okay? So this is the monopole term and the dipole term, and then I'm calling it a day. And then magnetic quadrupoles. All right? All right.
To get B, we cross this.
That's right. So ultimately, to get the magnetic field, we're gonna have to look at the curl of A. But let's just get A, and then we'll go for the curl of A. All right, so what is the trickaroonie? Oh yeah, that's the trick. Okay, so let me consider the divergence with respect to the prime coordinates of this tensor. So by our friend, the actually, let me look at one component of that. So let me look at the ith component of that. So this will be the derivative with respect to some other index, j sub k of x prime. Everyone see that? Okay? Because I'm taking the divergence here, and that only gets those components. So now I can use the product rule, and when I take the derivative of the first thing, what do I get? Kronecker delta. Thank you. And then what I'm going to get is plus xi prime the divergence of j. Okay? Because the partial k of that summed over k is the divergence of j, right? But in magnetostatics, the divergence of j is 0. And so, and this, I can sum over k, and then that's the ith component of that. So what that tells me is that the ith component, in magnetostatics, the ith component of the current density is equal to the divergence of this thing, okay? So what that tells me then is if I look at any component, let me look at the integral of any component of the current density. It's the same thing as the integral of the divergence of this over the volume. Okay. But what is that equal to? By the divergence theorem, it's equal to the surface integral where the surface is at infinity. And what is the current at infinity? 0. It's strictly 0. Doesn't even fall off. We're saying there's no current outside some range. So this is 0. And thus, since this is true for any component, ta-da! That term goes away. Okay? So that's 0. So the first non-vanishing term of the multipole expansion is dipole. There is no monopole as we know. Okay? So the first non-vanishing term is dipole. All right, so let's write down what that dipole vector potential is equal to minus 1 over c, the integral d cubed x prime, j at x prime dotted into the gradient of 1 over r. Okay, so we need to deal with that thing about who's it. Oh yeah, that's fun, doesn't it? All right. So, let's look at the ith component of this. Is that what I want to do? Yeah, I'll look at the ith component of this. And then I have a dot product here. I'll just choose K as my incidence. It's over prime. Okay, so this is summed over, and then I have that free index. Yeah.
So, to get to this point, to be clear, the only assumptions we're making here so far is that we're in magnetostatics and there are no monopoles.
We didn't make any assumption there were no monopoles.
Okay.
We just had the field equations that came from the del F equals 0.
Okay, so
Right.
then the only assumption we made was that this is magnetostatics.
That's
This
right.
is generally true for all those cases.
That's right.
Okay.
And now I'm just looking at the first possibly non-vanishing term, which is the dipole. Yeah.
This is not true for dynamics.
Yeah, we'll see about that. Yeah. It's more complicated. Yeah. One thing at a time. All right. So let's continue. I need to get through this. Okay. So let's talk about this. So we have this tensor. We play a trick here. I can take any outer product, say V, and break it up into a symmetric part and an anti-symmetric part. Right? When I add these two together, I get this. This is a symmetric tensor, this is an anti-symmetric tensor. Okay? So let's just do that over here. Let's look at this thing. I'll call this integral scripty I, right? Integral, sorry. So scripty I is equal to, and now I'm gonna break this up into the symmetric and anti-symmetric parts. So I'm gonna have the j sub I at x prime times xk prime plus jk at x prime x sub I prime. That's a symmetric part of this. And then I'm going to have the antisymmetric part. Okay, these two guys cancel and give us back what I had originally. All right. Okay, now I guess you ready for the next thing in this? Woo-hoo. Yeah, thanks. More vector identities. Okay, so aside, let's consider this lovely object. The divergence with respect to the prime variables of this vector field. Oh yeah, just that. So that's equal to the partial k I prime j prime as a function of x prime, j k as a function of x prime. Okay? What is that equal to? Again, we're in magnetostatics, so the divergence of j is 0. Okay? I'll take the derivatives, the first thing, and that's gonna give me a delta ki, so that's gonna become I. And then I can take the derivative of the second thing, and that's gonna give me everyone see that? Because the divergence of j is 0. Okay, so this is the symmetric part of that tensor. And if I thus integrate this over all space, what is this equal to?
So this is sin j,
Well, I have the integral of the divergence of something. It's a surface integral, which is 0, because the surface is at infinity, and this is the same thing. This trickeroony means that's 0 from the same point. So that means that this term does not contribute anything, and only the antisymmetric term contributes. So the dipole electric field, vector potential is equal to -1 over 2c, the integral over all the charge distribution, and then the antisymmetric part of times the partial respect to j, 1 over r. All right, we're close. We're very close now. This object is an anisymmetric tensor. An anisymmetric tensor is very closely related to a cross product. Okay? In fact, what this is equal to is equal to epsilon I, is it epsilon ijk or epsilon jki? I have to think about that, and I'm too lazy. Yeah, no, it is that. Yeah. If I let's put this guy there, then I know I got it right. Then it's this minus sign. This is equal to epsilon ijk
I mean, epsilon ijk and jki would be the same thing.
No, it was just I and j, there's a minus sign. Epsilon j I k versus epsilon I. Yeah. So, interestingly, I thus have the following thing, right? This is then equal to the, putting the epsilon ijk out front, and I can get 1 over 2c, the integral over the charge distribution, x cross j, the kth component of that, and then the partial with respect to j of 1 over r. So many cross products, so little time.
Partial with respect to r, 1 over r can be rewritten.
It can, but I'm not going to do it yet. What is this?
That first term.
Let me call this thing, for fun, m. So So this is N.
Negative M cross L.
So this kind of thing, if we look at this, let me ask you this question. What is epsilon ijk, aj, ek? This is equal to the kth component of the cross, or the ith component of the cross product. Right? So what is this thing here? It's the ith component of this cross product. And so what we have is that the dipole potential, and in what order? This is J and this is I, but I can write the other way around. This is minus M crossed into the gradient of 1 over R, where I told you this is messy, but in the end, we just use it. I have a 1 over 2C. I want to just conclude with examining this expression and what it means. This is the magnetic dipole moment vector. Okay? Let's contrast that with what we have for in electrostatics. The dipole electrostatic potential, which is minus P dotted into the gradient of 1 over R, where P is equal to the integral over the charge distribution of X times rho. Everything's the same except every dot product becomes a cross product. And there's some factors of C. But the point of this, as we will see, is that the magnetic field associated with this vector potential is the same as the electric field created by this scalar potential. They're both dipole fields. The vector potential and the scalar potential look different, but they produce the magnetic field associated with this vector potential is the same as the electric field associated with this scalar potential. It's the dipole field. Okay. Moreover, the dipole moment is related to something about how things are, the average position of things away from the origin. Here we just multiply the charge density by x, I could call it x prime. Here we have to cross it because what else would we do? But it's the same thing. Okay? And so we'll look at this more next week. All right? Very good.
Thank you very much. Get some rest.
I'm going to go to the airplane right away.
Oh.
Yeah. Yeah.